Testing, 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 testing. Shirt there. Did you go to the release party or did you get that after the fact?
I got it after the fact because I'm a size that didn't sell out immediately.
Yes. Nice.
I realized later I probably should have brought some of the rest of the camp shirts just like inside reference with everybody.
Yeah. All right, it's 3 o'clock, so I'm going to get started. This is Rust, system programming for web developers. Before we start out, I do have a confession to make. I am a Rustacean. So if you write Python, you're a Pythonista. If you write Ruby, you're a Rubyist. If you write Rust, you're a Rustacean. Not Rustafarian, Rustacean. And this little guy on my shirt is the official Rust mascot, a little crab, a Rustacean. And that's what I do at night. If you write PHP, does anyone know what you are if you write PHP? That'd be misguided. Actually, I kid. I write PHP during the day. I've been doing it for 10 years. But I love Rust. I fell in love with this language. And so I work at nordstromrack.com/hopelook during the day writing PHP and managing. And I write Rust sort of on the side. So before we get into Rust itself, let's actually talk about what system programming is. There's no definition out there that everyone's going to agree on about what system programming is. And those of us in the Rust community seem to have coalesced around this definition of system programming is when it matters. So I'll give you an example of when it doesn't matter. I'll pick on Ruby this time. Ruby is slow, but it doesn't matter because the database is the bottleneck. So when you're writing Ruby code, we're not calling that systems programming, right? Because it doesn't actually matter if Ruby's a little slower than where you're writing it in C because your bottleneck's the database, right? There are a couple characteristics that you're going to sort of see if you're systems programming. You're not going to have a garbage collector. You're going to have to manage memory yourself. You're going to have fine-grained control over your memory management. So we see that a lot in C or C++. and you're going to have zero-cost abstractions. So what that basically means is you're writing code that's sort of against the metal or against the hardware, right? You could be flipping registers on and off if you want to. You can represent a data structure in the exact size of memory that you specified. You can make entire programs sort of allocate memory on boot and then allocate nothing afterwards, running just on the stack, and then free up at the end. So you have a lot of control. So that is systems programming. And let's talk about why I think Rust is a great systems programming language and why I think web developers should take a look at it. Let's start with some history. So Rust is a language that's sort of been developed by Mozilla. It was developed with the primary use case in mind. See, Mozilla runs, as you all know, the Firefox web browser. And since the web is such a popular place nowadays, there's lots of events like Pwn to Own, where a bunch of security researchers or hackers will get together and they will present their exploits. And they do this with Firefox and Chrome and every single browser out there. And Mozilla sort of noticed this pattern, where all the exploits were basically coming centered on this sort of one vulnerability, which is a data race. And that would sort of happen when they would sort of have all these sort of threads running, they write C++, all this threaded programming going on to make Firefox fast, even though Chrome's faster. But they got all these threads going on, and there'd be sort of some mistake that someone would make with the way the threads are working and sort of sharing memory that would cause a data race. And hackers would take advantage of that and make the web browser do things like a remote command exploit, or they would they would make it do something like going to like a web page or fetching a resource that it shouldn't. And this was driving Mozilla crazy. They wanted to fix this. So Rust's primary motivation is to sort of fix this problem that Firefox was having about sort of not having some sort of safety checks around this, because threaded programming, even for the most experienced developer, is super hard. So what they did is they developed, they're working on developing now a web browser engine called Servo, which is sort of a replacement to Gecko. So if you don't know, Firefox uses the Gecko rendering engine to actually render out the HTML and the CSS on your web page. So they're not really building a new browser, but sort of building a new engine. We actually already see elements of Rust and Servo kind of being feathered into the existing Firefox browser. So before we get too far, I'm talking to a bunch of web developers, hopefully. Has anyone here actually written a Rust program before? Also a fair amount of Rustations in the room. That's great. Welcome. But if you're a web developer, you might be asking yourself this question, is Rust good for web development? And the Rust community sort of has this penchant for making these websites called like areweblankyet.com. And, am I on the wrong page? What's going on here? There we go. That's what I wanted. Yeah, areweblankyet.com. You can actually go this and actually talk about writing a web browser, a web service in Rust. And you can do this, but I think it's too early to tell if Rust is going to be good for web development. Rust is primarily a systems programming language, so we're talking about that. And really the problem with Rust in the web development context is that the web's made up of strings. HTTP is a bunch of strings coming in. Your database connection is usually a select with a bunch of strings coming back out to your Ruby or PHP or Python code. And really converting all those strings to types normally isn't worth it, right? Web requests, we hope, are under like 200 milliseconds. We're trying for expressiveness in our web code. We're using GC to kind of save ourselves from memory management a lot of the times. So it's just really not worth it to sort of do that. Also, we don't really need fine-grained control over memory because, again, we're only 200 milliseconds is our span. If there's some memory leak or some memory overhead, the request is going to be finished up quickly anyways, and we'll start over again. Also, Rust is a compiled language, so there's a compilation step. So we're not really going to focus on Rust for web development. I'm going to sort of slant this over to why web developers should sort of look at actually getting involved in a systems programming language. Yep, so Rust plus web developer, I contend, is going to can be a systems programmer, right? So let's talk about this. I think I did actually skip a slide. So Rust sort of provides these three constraints, right? Memory safety without garbage collection, concurrency without data races, and abstraction with the overhead, which we talked about is sort of what makes up system programming. And we're going to sort of go through these and how they can be applied to web developers. So I sort of have this, this basic theory, right? Anytime a new programming language comes out, There's a bunch of people will get on the internet and they'll say something like, oh, this language is going to replace all the use cases for this other language, right? We saw that with Rust too. Rust was sort of coming out. It was 8 years in the making. It's at 1.6 now. People were sort of discussing a lot, oh, do you think Rust is going to replace C or C++? I don't think that's really actually the case. If you're writing C or C++ right now, you're probably pretty comfortable in a language that you've been writing for years and years and years. And you might switch, but a lot of people, they have no reason to switch. They're working a day job using C or C++, and they sort of invested all this time and energy in getting familiar with that, and they can sort of, work through that. I actually think that Rust won't be a C++ killer. And I think instead, web developers are sort of the largest group out there right now of people in like the software developing community, and lots of new people coming in. And I actually think Rust is sort of well positioned, given some of its features, to actually be attractive to web developers and actually grow the overall pie. So there's really not a focus on actually cannibalizing that existing blue blue pie chart area of C and C++ developers. But I'm actually arguing, I think Rust actually can put a nice slice of new systems programmers into the community, which I think is sorely needed. And I think there's some historical context to this, right? I just didn't make this up out of thin air. We've sort of seen this. So, was anyone sort of was programming when Rails came out? Remember the same thing happening where there was a bunch of debate going on in the web development community, talking about would Ruby on Rails sort of unseat PHP as the dominant web language? Would it sort of take over? And you see these blog posts flying back and forth. Rails is faster and PHP is faster, and sort of it's never ending, right? And there are benchmarks lie. But what no one sort of understood at the time is cloud computing is in its infancy, right? EC2 starting to sort of get more popular. There's other competitors out there. We're virtualizing so many things. And you have a whole generation of ops people that they don't even know how to work in the cloud, right? They're used to procuring some hardware, setting it up, with some custom bash script. Maybe they're using CF engine. And then that thing's just going to run, and we're going to pretend it never shuts off. And if God forbid it dies, then there'll be some heroics going on. And what happened with the Ruby community, right? They're wanting to, Rails is new, people are coming in, they want to actually get this stuff in the cloud, and there's no tools for that. And then the Ruby community finds out is Ruby's a great DSL, and they start writing the tools themselves. And all of a sudden you get things like Capistrano for deployments. You get Puppet and Chef as a much better replacement to CF Engine for configuring servers. You have multiple sort of ways of running multiple Ruby versions in development, and even, God forbid, production if you wanted to. You have awesome sort of developer tools like Vagrant, which is a Ruby script around VirtualBox that makes life much easier for us, and things like Sensu, which is a Ruby replacement for Nagios. So all these great, so Ruby didn't create the DevOps movement, but certainly what they were doing, they found that Ruby wasn't replacing PHP. It just actually created this entire generation of DevOps people that have built a bunch of tools that basically everyone in web development community uses or has been influenced by. So that sort of happened. We kind of see it actually going on now, right? You take a UI developer, slap some Node on them, all of a sudden you got a full stack developer. But why is this, right? So I was a PHP developer when Node came out, and I remember looking at Node going, why? Why would anyone want to do this? And a bunch of other people who were writing Python and Ruby said the same thing. What's going on here? And Node is a new technology, right? Nothing that Node sort of brings to the table is brand new. We've been able to render JavaScript on the server for years using Rhino. We've been able to do async I/O using libev, I think was that what it was, before libuv was created and used in Node. So there's no new technology here. It's been around at least a decade. Why all of a sudden, is this such a powerful movement? What's going on here? And if you sort of think about web's eating the desktop, right? And if you're a UI developer, your requirements being given to you are hey, make the web feel like it's native. I want fast and everything dynamic. I don't want to reload the web page. Just make everything single page apps, Ajax load everything. So these UI developers are writing HTML and CSS and JavaScript. They're going to the Ruby person and they're saying, hey, I need you to give me a lot of this event-driven sort of interaction. I need you to do a lot of this stuff for me. And they're going what are you talking about? I know REST. That's all I do. And they're no, I want WebSockets. I want all kinds of nice interactions. And there's this friction. right? So with Node, all of a sudden you took a UI developer who was fighting with their backend engineer, and you're like, hey, here's all the tools, you can just do the whole job yourself. You already know JavaScript, here you go. So now all of a sudden you have a full stack developer, and it's happening right now. And for a long time, the server-side people just didn't get it. You saw blog posts like Node.js is a cancer. People putting up blog posts like, hey, Fibonacci runs really slow in Node. And as we all know now, it's more of a mature ecosystem. Like, it's really powerful. It's really good. It complements a lot of what people are doing out there. And it didn't, so no one lost their jobs doing PHP or Ruby or Python development. But what you have is a whole generation of people who are only working in the browser, now working on the server side as well, and providing a lot of influence in the community. So I think the same thing is going to happen with Rust, right? You're going to actually have you can have web developers, and you're going to sort of convert them into systems programmers. And that's not to say you're going to stop being a web developer. You might actually just do both. Like, you're just going to sort of, let this sort of enhance your tool set. And so, and why do I think this is needed? So as we all know, like 10 years ago, we were building monolithic applications, right? One repository, a web server, maybe your runtime behind that. And if you wanted to scale that out, all you kept doing was horizontally scaling, right? Spinning up more VMs or procuring more hardware. And that's, unless you were like the 0.1% of the industry, that's basically how you scaled. Throw more databases behind it, read clusters, right? Now, even sort of the average sort of engineering shop has microservices and all these different parts of their application. And if you start going through like some of like the concrete examples of each of these, you're going to find out like none of them were actually written in the languages web developers know, right? Yet we're highly reliant on them. So if we're talking about application caching like Memcache or Redis, both written in C. HTTP caching layers, Varnish and Squid. Job queues. I think Rescue might be like the one example here if you're in the Ruby community where you have like a Ruby sort of implementation of a good job queue that you can use. If you're in Python or PHP, like, no, you're using something, you're using like Gearman or Rabbit. Relational NoSQL databases, these are all written in C or C++. Search databases, the next other exception here, those are written in Java, though any ops person hates this because, when you're running high workloads and the GC pauses on you at your most critical time, you're getting really mad, and so you fight with it nonstop, and every ops person wishes that these are written in C or C++. Load balancers and VMing containers, like we're all like VMing and Dockerizing everything under the sun right now, right? Again, all written in a non-web language. So we're highly dependent on this entire ecosystem of software that web developers have basically very little access to. And what you basically have is this massive knowledge gap, right? Only makes it worse that all this stuff is open source. So there's really no one getting paid to do this stuff, which means you have very, very few people actually working on this open source software that actually have the know-how because it's C or C++. And this is bad for a few reasons. One, like we've seen burnout in the community. Also, we've seen that a lot of these maintainers don't have time for things like important ancillary tasks like documentation or putting out proper releases and things like that. Also hinders the state of the art. When you don't have people sort of like fresh people getting into a certain area, sort of a couple winners emerge, and then things sort of stagnate, right? We saw this with the web browser for a while, where where web developers weren't actually involved in the web standards. You had a bunch of C and C++ people that were developing browsers, sort of figuring out how APIs and the web worked. And when they would come out, all the web developers would say, like, what are you doing? Like that does not match your use case at all. Only recently do people in the web community have they started joining TC39. We've been getting things like ES6 and ES7. Like, that wasn't an accident, folks. Like, it really took web developers getting involved. I think, likewise, we're missing core use cases in the web community because we're not getting involved to solve parts of our web stack for ourselves because we know best. And there's a clear example. I write PHP during the day all the time. PDO is the sort of the database adapter abstraction in PHP. It means PHP data objects. The person who wrote that is a C programmer. He doesn't write PHP. And the way he wrote it in the constructor of PDO, when you do new PDO, what people normally do in the bootstrap, that actually makes the network connection to the database. Like, no web developer wants to make a connection to the database in the bootstrap of their code unless they're explicitly saying it. And you have to like kind of work around this as a PHP developer. Like, everyone has to do it. It's crazy, right? And it's because I think, Wes wrote a great library, but he missed a core use case because he wasn't actually involved in the PHP community. So Oh, go ahead, I'm sorry.
I was saying, I think you're overdoing the sales job. If let's say you're dealing with a time machine like an APR or something, where you can see what can ever, it's either C or this. So if anybody's going to build a web interface or something this small, they have to do this.
Yeah, I think for the video, saying I'm overselling it. I'm sort of laying out sort of like the background of why I think web developers are getting involved in Rust now. And we're going to go through certainly a lot of code examples, but I thought sort of the history was important to sort of present. Yeah. So there are some barriers to entry for web developers to get involved in systems programming, right? Why haven't people, and this is why I think I want to set this up. Like Rust is fundamentally different here, right? Web developers aren't getting involved in C and C++ because it's unapproachable, in my definition, right? There's a problem with memory management. When you can sort of compile your C program and it compiles fine, and then you put it into production, and all of a sudden it seg faults on you at the most critical time, like you're not going back. Like that's a super painful experience. And so if you're a web developer trying to get something done and try to get this critical task out, like that's not making you look good. C or C++ sort of provide that foot gun for you. And you can't sort of rely on GC if you're doing systems level stuff, as we discussed. And I think a lot of web developers don't want to write C or C++ because it's not an expressive language, right? When we write Ruby, we like how expressive it is. When we write Python, we like not having to do semicolons. And we shouldn't have to necessarily give all that up if we want to write systems programming. And a lot of times we don't need types, and we've kind of grown accustomed to not having types. So Rust can kind of solve a bunch of that stuff, right? So these are the 3 tenets of Rust, and we're going to go through and talk about how they allow you to do memory safety, give you fine-grained control, which is your cake, and sort of not let you segfault, eat it too. We're going to show, I'm not going to get too much into concurrency because it's hard to show in examples, but we will get into a lot of abstraction without overhead. But I do want to make sure everyone understands, like, I think 2 is super important here too, because as we know right now, we're taking a single piece of hardware, like a server, and we're breaking that down into virtual machines and Docker containers. I think at some point pretty soon here in the future, we're going to see a lot more use cases for something like Apache Mesos, where we're taking actually multiple machines and trying to make them work in concert together. And right now, trying to do that, if you have architecture that's horizontally scaling, you sort of know that that actually is a lot of time and effort to make sure those things are coordinating correctly. So having concurrency without data races is super important, I think, for sort of the future where a lot of this system stuff's going. All right, so let's get into some code examples. Rust right out the gate has basically this concept of ownership, which allows us to sort of have memory safety without garbage collection. We're going to go into some examples of how ownership works. So I'm going to start walking you through Rust syntax with the examples. If any of the syntax doesn't make sense, let me know. But in this example, we're defining a function take that has a single variable v of type vector of signed 32-bit integers. And then below that function, we're going to actually define a variable v that is a vector of 1, 2, and 3. And we'll pass that variable v into our take function, and then we're going to print out below that the first element of v. In any other language that you've probably been exposed to, this is perfectly fine, perfectly sane, and perfectly normal. It'll compile, it'll work, it'll run. In Rust, this is an error. And it all comes down to ownership, right? We actually passed our v into the function take. And once we did that, we have given up control in that scope of using that value v again. I'll show you the code again. So line 3, once we pass v into take, we are no longer allowed below to use v or access v anymore. And this fundamentally, like there's references, there's other stuff that Rust introduces here, but this fundamentally is how Rust gives you memory safety without sort of the garbage collection piece here. It basically ensures at compile time that you're not doing anything that would basically cause problems, right? And this is really nice because it solves a whole class of problems that C or C++ don't solve for you. You don't have segmentation faults anymore because you're not basically allowed to sort of use after free, essentially, right? Or even use before you even allocated it. The compiler is sort of using this rule called like the borrow checker. It's using this borrow checker is going through and basically making sure at compile time you're not doing anything that would basically blow up your program at runtime. And you also don't have memory leaks anymore because Rust is sort of handling the freeing. After it's allocating, it's also handling when it's supposed to free. So you don't have to worry about this whole notion of I need to have functions that are dedicated to allocating memory, and then making sure I'm only freeing that memory, and then nothing else is sort of accessing it, right? And if you've written C++ before, you know this is sort of just a chore to do, and Rust does it for you for free. The problem is when you sort of start out with Rust, you're going to start fighting the program, because as you saw, like that was a perfectly valid program that we wrote, and we all know that like that's how we write code, and Rust doesn't let you do that. And so when people start writing Rust, they normally start fighting the borrow checker. And I'm like, no, that's perfectly normal. I do that in like this other language. Why won't you let me do that? And really what's going on here is the borrow checker isn't doing anything actually that you shouldn't be doing. If you're actually like a grizzled veteran C++ developer, you basically have internalized like these conventions of the borrow checker into what you just sort of know. Like it's like tribal knowledge to you. You go through and read like some like the best C++ development books will actually like outline these steps, like make sure you do all these things. And what Rust did is basically codify that into a compiler. So what Rust is, when you're fighting the borrow checker, kind of take heart in that you're kind of making an investment, and that the compiler is literally teaching you, painfully at times, because it doesn't care how frustrated you are and it doesn't actually go on vacation, but it's teaching you to become a systems programmer. And you could actually take those same rules and apply it to other systems languages and be just as successful. One thing I actually really like about this too is you can contribute back with confidence, right? How many people have sort of wanted to put a patch into a large program, either at where they work or even in open source, and have kind of felt a little uncomfortable about actually pushing that pull request button, right? Because even though like the tests pass, like you're like, I don't know, like it might blow up at runtime. I might have missed something, right? And it's kind of scary, especially if you're new to that community or you're a new developer. Even if you're seasoned, you look like a knucklehead if you just sort of miss some obvious thing, right? And the great thing about the borrow checker, even though you're going to fight it at first, you're going to get to the point where like when that program compiles, you pretty much know that it's going to work. And if it does blow up, it's not going to be for some obvious thing. It's going to be for something kind of crazy. And so like I myself have contributed to Rust core. And I'm not like that good of a programmer. But once the thing compiled, I just felt like I can push the button here. I can actually send this patch over the wire because like the compiler told me I'm a good systems programmer and for this particular piece of code. Cool. So great. So now this is why Rust is so compelling in terms of writing safe code, but I did talk about we don't want to give up some of those aspects of scripting languages that we like, right? So let's get into some of these things that Rust does so that we don't look like we're actually writing so much sort of C or C++ code. So Rust spends a lot of time on ergonomics, and we do think writing the code should be as enjoyable as writing it in a systems scripted language. And we want the compiler, we use the compiler to figure out all this borrow checking stuff, right? All this ownership stuff. And we also use the compiler to figure out all this sort of boilerplate stuff that you might do in other languages that have strong types, and we just sort of let the compiler infer it. The canonical example here is like in Java, right? You have to define the types on both sides of the assignment. It's like, why? I just defined it on one side, just figure it out on the other side. And what we end up doing, right, is instead we purchase IDEs that basically fill in all the boilerplate for us, right? And instead of using IDEs, Rust, let's just stick it in the compiler. So here's an example, simple example. We're going to define some variable foo that's going to be of typed signed 32-bit integer, and we're going to assign it to the variable 5. And as humans, we can all reason about very quickly, like, that's a number. I don't need to specify the type, so neither does the compiler. And this looks like a lot of languages that are like scripting languages, right? Let foo equals 5, no type necessary. That's great for like type, like assigning like variables of types. We also can go one step further. The compiler can even figure out, in certain cases, how to even default the return type. So here, we're getting a little more complex. This is how Rust defines a closure. So we're going to define some variable f, and it's going to define a lambda function that takes in a single variable x of type signed 32-bit integer. And it's going to return a signed 32-bit integer, and it's going to return x. And this is an example of the identity function, if anyone's curious. And this is how you write a closure in Rust, or a Lambda function in Rust. It's pretty terse. We can even get better. That is how you can write that same function in Rust. And again, that looks a lot like a scripting language. So you can go through a lot of your Rust code and not actually worry about specifying the type. And that's nice because, I'm sorry, go ahead.
How does the compiler know that that's assigned 32-bit integer? Can I pass in a string?
Yeah.
Return a string?
So I'm going to say that by actually writing it, so not only is it nice to not have to write the type, in certain cases, this is actually more expressive even to your code, because you can use the same function to actually allow multiple types come through, and the compiler will know that. So it's even actually better, like this is encouraged, right? As programmers, we're sort of taught like laziness is a good thing, and here it's showing up in the positive. All right, and we're going to go to a little more complicated example. These apostrophe A's things are called lifetimes. And so what we're doing here is we're defining a function that's very similar to our identity function called silly. And I'm introducing this concept. I'm introducing a lot of concepts here, but ampersand means reference. And that lowercase str is a string type, one of the string types in Rust. So we're passing in some variable s of type string and as a reference, and passing that reference back out. And we see like these apostrophe A's, all of Rust's functions require you to sort of define these things called lifetimes. And that's how it actually figures out how long things like references should live for. It's all really complicated. You have to be like, some programming language theorist to actually figure out a lot of times when certain lifetimes can be used. But the great thing about Rust, again, we're using the compiler. Like 99% of your code does not need the lifetimes at all. The compiler infers it. This is actually really nice because we get all the power of lifetimes without having to worry about it. So if you're a new developer and you're trying to do something in Rust, you don't want to have to start thinking about lifetimes. You're trying to just get something done, right? And so the default here is lifetimes. Lifetimes are there under the hood, but they're just sort of like inferred for you. And when you want to actually turn on like the advanced switch, like you can switch that advanced switch on and start telling Rust, no, I know exactly what I'm doing. Here are my lifetimes. And be really explicit about what you want to do. So you get all the control with sort of none of the penalty. All right, at this point, we sort of kind of kept it pretty introductory, and I've been introducing a lot of things that are probably pretty basic. We're going to sort of step up a notch here to a little more theoretical stuff that's going on. If anyone has any questions, please stop me and ask. So, optional correctness. Yes, go ahead. Great. So the question is the borrow checker a reference counter? No, it's not. The borrow checker is a program that there's by default there's no sort of reference counting going on. We're literally at the metal level where like C is. It's just there's a couple phases in the Rust compiler. This is the first phase that it goes through and just sort of makes sure the semantics of your code aren't violating sort of any of these constraints. But so it's not a runtime thing. It's done at compilation time. Lifetimes, yeah. Think about lifetimes as basically it's less of a scope. It's almost like typifying sort of how long a reference to a variable should live. Lifetimes are one of those things. I introduced it. It's going to come up if you're getting into Rust. You don't need to actually worry about them hardly at all, but you kind of want to know what they are in case you run into something when you're using a reference. I would say most people have written Rust and they'll go months without ever needing to put one lifetime in place. So they're there. Be aware of them. Don't be scared of them. All right, optional correctness. One of the things I love about Rust is it sort of takes this nice balance of theory and applying that theory to actually real-world problems. And as we know, the real world is not always sort of on our terms. And so, I like a language like Haskell. It's great, but you have to jump through a lot of hoops sometimes to make your programs work. And I think Rust strikes this really nice balance. I think we can sort of a great example of this balance is in Rust, you can do really return types, right? So we've all seen this type of code. We're going to let R equal the value of some function, the return type of return value of some function. If R is an error, we're going to return early, return false, and then we'll go down our happy path code, right? We all write that when we write like our normal code, and we write that in Rust too. But Rust also has this monadic type, right? We're going full burrito now. This monadic type option that can wrap a type T, so any type T, it can wrap this. And if you're not familiar with option, it's like the either type in Haskell. Option can basically say, look, if there's something here of type T, or there's nothing here, right? So it kind of maintains these two states. And if you're going to go like to programming language theory sort of side of things, this is a monadic type, and monadic types are not allowed to return early. Rust is like, whatever, you can return early. So what we have here is an example. Let variable foo equal some string bar, and we're going to use the find function on foo to find the character b, right? And this match statement in Rust, it's kind of like a switch statement, right? But it makes sure like you sort of cover all the different use cases. So as I said before, option is either there's something there or there's nothing there. So if there's something there, some character C there, then we'll just return C back to our variable. So C, is where that position is. And we're good. And that's what this code is going to do, right? We can have a different example where our string is nope, and B's not there. And we're going to go into this other branch of code, this other arm of our match statement, where it's none. And we're going to call this macro panic, which basically means like fatal error, bail out of your code, stop running the code. It basically return early type. So, when people sort of, if you're a programming language theorist, you see option, like, I love monads. But Rust is like, look, you can return early too. So you kind of get all the power of monads, but sort of all the simplicity of sort of returning early. Which is just easier, right? Like, you don't have to like sort of contorting your code to say like, okay, I get only one return type at the very bottom of my function scope. You're trying to figure out how you can break your functions into even smaller functions to deal with sort of the different if-else statements that need to happen. It really makes things much more approachable. And this pattern right here is so common in Rust that they actually made it even easier to do. And they have this method called Unwrap. So this is the same thing as before, that basically Unwrap will say, look, if you found what you were finding, I'm just going to return it to you. And if you didn't, I'm just going to blow up the code. And I'd be like, man, why would Rust put that in there? I thought you said this was supposed to be like memory safety and like really good systems programming stuff. Well, it's true, but if you're starting out in Rust or even starting out trying to solve a problem, you're not worrying about correctness, right? You're trying to hack your way from like start to finish and get something compiled and something generally working to see where you're at, right? We don't normally explore new spaces by doing TDD first, right? TDD is after you've already sort of mastered your Ruby or your PHP or your Python. TDD is when you're sort of just trying to, you're on Rails. If you're starting out Rust or sort of exploring some unknown problem where you're trying to figure out like some weird protocol and you're twiddling bits, you don't want to be dealing with TDD, right? No, you don't want to be dealing with really correctness either. You want to turn that off, and so you can use Unwrap. So a lot of times what people do is they'll write their code and they'll just do their first pass, and everything will just be unwrap, unwrap, unwrap. It's fine if it blows up. It's not production ready yet. That's okay. And you can go back later then and actually say, like, I'm going to now actually handle like errors properly. Log them. You're going to bubble them up. You can do all these different things. So it's really nice. Again, a pragmatic approach. And really, I think it goes down to Rust sort of says, like, the programmer knows best. Like, we're going to sort of put all these defaults in place, and we're going to sort of set this really nice system programming language up, but the programmer knows best, and we'll sort of allow them to sort of override things when they want to. So much to the point that Rust also has this notion of unsafe, where I sort of told you before you had to satisfy the borrow checker. If you wrap code in unsafe, borrow checker says, I trust you. So here's an example where we're actually creating the sparkle heart emoji out of a vector of bytes. And we're saying, like, look at Rust, trust us. These are valid UTF-8 characters. If they're not, then that's on us. And what this is sort of nice is, like, again, it allows us, if we're trying to really take theory and apply it to the real world, sometimes the real world is not on our terms and we need to do something crazy, right? In this case, we're sort of demarcating, like, I need you to trust me right here, Rust. And also to all the other developers out there, like, hey, I need you to trust me here. Rust doesn't have my back here. I'm saying I got this. So let's talk some about zero-cost abstractions, what I sometimes call mullet-driven development. You're going to get all of sort of the expressiveness, or actually all of it, a lot of the expressiveness of Ruby. So you get sort of the Ruby in the front when you're writing your code, but you don't take any of the performance costs. You really get like C in the back, right? This is great. So let's go through some examples here. Right here we are defining some variable n and then taking a range of numbers 1 to 10. We're first mapping them. So we're multiplying all those numbers by 2, then calling filter on them. So any number greater than 5 we're dropping, and then we're adding those all up with our fold function here with an accumulator. This looks very similar to something you might write like in Python or Ruby, right? And this, like, if you're like, you know, a little cutting edge Rubyist at this point, like you're like no for loops ever. I map everything. It's great. You can sort of do the same thing in Rust. But if we wrote this in Ruby, right, like first we're going to basically loop over every single one of those numbers, 1 to 10, once for map. And then we're going to loop over the numbers again for filter. And then we're going to loop over the numbers again for fold. And that's going to be basically 3n times. Now, if you write Ruby, again, it doesn't matter because that's not what you're trying. You want expressiveness. You're not trying to optimize your code for performance. You want expressiveness, maintainability, readability, and we take that hit. We don't care. But if you're writing a systems program, you do care. So what actually, this is valid Rust code. What Rust is going to do under the hood is take map, filter, and fold. Instead of doing those 3 iterations, it's actually going to create like a single loop and actually do all that work in a single pass-through of 10 iterations. It'll actually inline map, filter, and fold and sort of do that in sort of one shot. And so you don't need to worry about it. Like if you want to write your code expressive and make it really clear what's going on, you don't have to go back later when you want to optimize it and sort of make it almost unreadable. Has anyone ever looked at the OpenSSL code base before? Like you wonder why there are so many bugs in that thing, right? They're trying to make the thing fast. And when they do that, it becomes almost unintelligible what's going on. Here, we can make it really clear what's going on, yet still get all the performance out of it.
Could you add more methods like that as a user of the language that like kind of inline together like that?
The question is, can you add sort of methods like this as a user of the language? So the nice thing about Rust is Rust is written in Rust, and these are just iterators. So you can write your own iterator methods and sort of do this yourself, and people do this all the time. Further question? Yeah, sure. The question was, why does filter take a reference instead of the actual type? The reason why filter takes a reference is it doesn't actually need to own the variable to it just basically needs to sort of use the variable to check something real quick. Unlike map, map might actually mutate the variable. Filter is just sort of peering into it, so you don't actually take the variable. You just take a reference to the variable. And that's common like in the generic filter method, right? So these are all like immutable things. So you can make map take a reference if you really wanted to. Other questions? And then we can even go one step further where Rust really does have first-class functions, like a JavaScript type language, right? I wrote some code. I created a simple REPL, read, evaluate, print loop for Rust. And this is what my main function looked like. Again, systems language, where our read, evaluate, and print are all functions. And again, the compiler using LLVM compiles this down, and we're taking no performance hit. And we're getting sort of all the monadic stuff going on in here with the and thens. We have all the expressiveness, like it's very easy to see what I'm doing here, and all the speed of C. Let's go one step further with generics. If I define a function here first, and if you're familiar with like Java or anything like that, we're defining a generic type A and a generic type B, and creating a tuple out of those values. And we're basically just saying like it's going to return that type A. In the body of our function, we're just saying for that tuple, just return the first one. So that's what the function's doing, right? Very simple. Most languages have to do this at runtime, right? Like if you do this in Java, Java is actually figuring out at runtime like how to actually like figure out all the typing stuff. And you can run into some problems there where it can actually not figure it out. So for Rust, we can do the same thing like you can with any other generics. We pass in integers, you can pass in strings. And even when we do this in something like Ruby or PHP or Python, it's doing this at runtime. We just never see it. It's a hidden cost, right? Actually, what Rust does is it has this concept of monomorphization. Long word, don't have to remember it. But essentially what this does is the compiler creates a specialized function at compile time for sort of each type, right? So if we're passing in if we're passing in an integer, the compiler goes, oh, I see you're passing in integers in your program. I'm going to go and create a specialized function for integers. If you're passing in a string, it's like, I can see you're passing in strings as well. I'm going to create a specialized function for strings. That can look basically like this. Like, you could do this yourself too, right? You can write specialized functions. Rust does this for you for free. So you don't have to actually, you can write really generic code. We saw with our closure example earlier. And under the hood, it's creating these specialized functions for you that you don't have to manage. It's just like, I got this for you. So again, all the expressiveness of sort of a higher order language with none of the sort of the performance cost. Is there a question? And this, the question was, could you have a string and a numeric? I am defining two discrete generic types, so you could. I didn't show that example, but yes, you can kind of do any sort of generic stuff, typing that you want. Great. And then let's move into another topic here. So systems programming, we might think if you want to become a systems programmer or write a systems program, you got to write the entire thing in sort of that language, right? It's all have to be in C or all Rust or all C++. And actually, I would argue systems programming doesn't sort of, the definition doesn't actually require that. What we can actually do still is write the bulk of our program in something like Ruby. And then once like we're done writing that program, we can actually go back and figure, like, is there any like really slow bottlenecks that are not I/O bound? Any CPU bottlenecks? And if there are, we can actually drop Rust in to actually solve that problem. I actually did this. There's a library out there called Selecta, which was written by Gary Bernhardt, which is a really nice sort of little command line utility that allows you to quickly search your file system for things. It's really nicely written and has like a full TTY and all this support. But there was this one hotspot in the code where there's this really efficient search algorithm, but because it was Ruby, it just could never run fast enough. It was always like the biggest bottleneck in the code. I actually just took that library, rewrote the search algorithm in Rust, and put it back in, compiled it into the overall program in Ruby, so Ruby could just call my Rust code. And we can do this because Rust treats C as sort of the common language across the entire ecosystem, which is basically true, right? And Rust interacts with C really well. I'm not showing an example here because it's a fair amount of code to get it going, but there are a lot of examples of this on the web. On my blog post, I have one for PHP. Again, I've written one for Ruby. It's fairly approachable. There's some, obviously there's like some boilerplate work to sort of tie into those C interfaces that are sort of defined. But Rust makes it pretty easy, and because you have all that fine-grained control. Rust isn't like a GC language, right? If you try to do this in something like Go, which Go is a great language, but Go has a GC in it. And if you're trying to match Go's GC up to Ruby's GC, what do you think is going to happen? Like, not good things. Because Rust doesn't have a GC, just like C or C++, you can easily tie into this. Even Node. So what recently came out too was an example from someone at the, I remember his name now, at Mozilla actually put a whole blog post about how you could actually tie Rust into the Node.js runtime, which is written in C++, a little bit harder than C. Let's see here. So I went over a lot of concepts. It's really hard to sort of go through some of the code examples here, but there's a lot of sort of ways you can sort of start digging into Rust. I don't think there's actually a Rust book out yet, but the documentation on the website is great. Steve Klapnick has done a great job. He's actually employed at Mozilla and does that full time. But I actually think an even better way to learn Rust is to come to the Rust Los Angeles meetup. I actually run that meetup. We do things like last month, there's a new program out there called Stockfighter. If anyone's heard of Stockfighter before. And it's basically a game where you write an automated stock trading program. And it's pretty real. It's not 100% real, but it's pretty real. And believe it or not, no one had written a Rust SDK for it, so we're writing a Rust SDK. And really, I think the hardest thing about, with any of this stuff is getting started, right? Rust lowers that barrier to entry to get started a lot, but there's always sort of something that doesn't make sense. And so if you're with a bunch of other people, those questions get answered really quickly, and you actually feel like you're making a lot of progress. There's the website on there. And again, reach out to me if you have any questions. That link at the bottom is a link to all my blog posts on Rusts, and there's actually a number of them on strings. So if you do start writing Rust and strings are frustrating you, go ahead and check those out. It should make things a lot more clear. But feel free to hit me up on Twitter or GitHub or anything if you have questions as well. And with that, I'll open the floor.
When I said the other side, what I meant is Rust can be a very easy choice when you have a very small device, which is what I'm interested in. Do I have some way which at least I can generate a Rust executable for an Arduino compatible, or an AVR8, or some other small controller?
Yeah, you can. There's actually, the question was, can you generate a Rust program for something like Arduino? Rust recently in 1.6, which just came out, actually has stable support for not including even the standard library of Rust, only just like the bare of the core components, which allows you to compile it for things like the Raspberry Pi or Arduino. And basically, the footprint's very light. You get just the bare bones. And then it is. I realize that. You still can do it for the Arduino. The Rust compiler has compiler targets, and you have fine-grained control over the different compiler flags that you can send and make, and you can sort of compile it to anything you compile C to. The question was how small can the Rust binary be? Yeah, so Rust Hello World is a little bit larger than you might think, because again, it's doing a lot of that sort of specialization under the hood. Again, if you need to optimize something, you can do it Unsafe. I don't remember off the top of my head, but I know it's a fairly large Hello World. They have not tried to optimize for the Hello World example. I know some people have been interested in that, but it's kind of a red herring. I think once you get into something that's beyond just a simple program, it sort of gets amortized out, and you're basically sort of on par with C or C++.
You can make something that goes under 50K.
Don't quote me on that. You could certainly ask on the Rust users forum, and they would be able to give you some direct examples. I think there's been some talk about that. So I'm not into that space as much, so I'm sorry, I can't answer like definitively. Yeah. But certainly it's of a lot of interest to the Rust community, embedded programming, stuff like that. Other questions? Joel, and then...
So you mentioned that OpenSSL in particular is a complicated piece of software. Do you see someone taking up the Rust to do actual security for crypto software?
There is a Rust libraries or user libraries in Rust are called crates. There is a Rust crate that's starting to replace parts of OpenSSL. I think, Rust is 36 weeks stable. It went through 8 years of basically prototyping to solve that main core use case of Servo. So we've been 36 weeks in production mode, like a 1.0 release, and we're in 1.6 now. And I think really the community is sort of looking at things that form like a 10-year frame of reference. So I think we'll see more adoption of those things as they come. But sort of things are kind of going slow as we're sort of figuring out things like higher kind of types. I think as we sort of figure out more and more things within the community, you're going to see more adoption and see things like an OpenSSL port to Rust or other things like that. I myself do a lot of work with a library called Mio, which is a replacement for libuv. So it uses things like equal or KQ if you're on BSD. It's a complete Rust replacement for libuv. That is, I think Dropbox just put out. That's what they use to sort of create their hard drive mesh and to figure out how to load balance all those different files across your system. So it's coming, and some people are really interested in doing that because it's nice to write in. So, your question.
Can you talk more about concurrency control in Rust?
So the question was, can we talk about concurrency control in Rust? Yeah, I would have to dedicate 10 slides, I think, sort of to walk through just how that sort of works under the hood. There are some examples up, but essentially, Rust is using the borrow checker, and you can sort of reason about how you're allowing threaded computing to share memory via the borrow checker. And so it does that all at compile time. So it's using those same semantics to sort of enforce that you're not going to step on a piece of memory. So once one thread takes ownership of a piece of data, the other thread just can't. You don't need semaphores or mutex at that point, right? They are, and then you can actually use a lot of other semantics about like when things get freed up or out of scope to pass back ownership upstream to a different thread. So like there's a really good way you can like do that with channels, for example. It makes it really easy.
Is that better than Go?
So the question was, is that better than Go? So Go is focused more like on their like Go routines, right? And they do have channels and stuff. I believe the last time I checked, the Go routines actually leak a little bit of memory in order to do a lot of their safety guarantees. So again, Go's a great language. I think it's it has a lot of use cases. I think to replace a lot of Java stuff for like web servicey. It's like kind of lighter weight than Java. I think that's where it really shines. And again, you don't really care about if there's a little bit of leakage there, right? But there are coroutines in Rust. You could do the same thing, but they just sort of have different strategies. Again, Go has the garbage collector. Yeah. Other questions? Here, and then we'll go back to you. When is the next Rust? Yes, the question was, when is the next Rust meetup and where do we meet? The meetups are usually in the middle of the month, so it's whatever that Wednesday in the middle of the month is. And we meet in the Nordstrom Rack / Hopelook production studios in Culver City. And if you go, the website has like a huge thing of directions, so you can get there. But yeah, check out the website, has all of that information. Hope to see you there. Question?
How do you see Swift affecting the acceptance of Rust?
Yeah, so competition's good. I actually don't think it's really going to impede it too much. We've even seen like in C++, a lot of stuff that we've been doing in Rust, the C++ community has been trying to do to like take on as well. And there's actually now some sort of certain pointer types that sort of have some kind of ownership and properties that Rust has been sort of messing around with, right? If they're already like things like own pointers in C++. I think Swift is going to sort of make it more, make things more accessible. You're going to get a lot of people who were writing iOS apps, starting to write actual server-side stuff like in the OS X ecosystem. So I think actually it might only speed up adoption of something like Rust. They have a lot of similarities, but they also have a number of differences too. That the Swift community says, like, we're not trying to compete at that level, or that's sort of some of the way we're compete in some of the areas where Rust is trying to compete. Another question.
Yeah, do you feel my experience with other developers is a lot of people tend to struggle with functional language. Do you feel that's a restriction for a lot of developers? Especially because you're introducing this to mostly web developers here, which they're programming PHP and Python, and not a lot of it really focuses on functional language, but Rust is primarily a functional language. How do you feel?
So the question is, if the difficulty of functional language semantics would be a blocker for the adoption of Rust. So Rust actually is an expressive language, not a functional language. So it actually can do a lot of functional things that you find in other languages. But every single thing that you do in Rust is an expression. What I mean by that is you can actually assign a variable to the result of an if statement, which is actually after a while quite natural. So you can write your code in Rust in the most basic imperative form that possible, just straight like almost in that classic C style, right? Which is a bunch of functions, and that you just sort of cobble it all together and make a program out of it. So again, a lot of the stuff that we talked about is opt-in. You don't have to take advantage of like map and filter and fold if you don't want to. You can actually just write just normal functions and it'll work just the same. So I actually don't think that's too big of a deal. I think it's really more of an upsell that it can do those things. Because I think most people sort of want sort of a higher order feel to the language that they're working in now. Question? The question was, does Rust have exception handling? So Rust does not have exceptions. It does have a macro called try, which at first glance might look like throw in deal with exceptions. That's just bubbling up things like options or result types. But the language designers made an explicit decision not to sort of add exceptions into the language. Panic, and though the things look like exceptions as well, like they'll sort of quickly abort the program. But yeah, I don't think there's any plans for exceptions in the language as well. That's sort of a hotly debated topic, but that was the decision. Any other questions? All right, well, thank you so much for listening to the talk. I hope to see you at the meetup. Yeah, 4 minutes. How's it going? I think Python's great also because, like I said, it might use that strategy to write it. And then either works with Rust is really needed for like, for example, Memcache is really good for Perl. And you can kind of use that same strategy. You have to kind of do like a rewrite, right? You can really write a portion of using Rust. I think some people, like myself, like I can be as I get into Rust as I can. So I'll do that out the gate. But it's not a very tough to sort of really like your progress to try. Also sort of really thinking of like the box, so if you're trying to iterate faster and using like at work, federated in small pieces.
There's a holy word.